my name is Josef Svenningsson, and I might as well continue talking about myself. I work at Ericsson, but the reason you're not seeing any Ericsson logos here is that this is my spare time project, and Ericsson doesn't own this, and they don't pay me to do this. So, and it's all open source, as I will show you. But yeah, so that's the reason why there are no logos or anything. So I was. To be frank, I thought there was only going to be 3 nerds in the audience here today, and I'm really pleased to see that it's packed, and also that yesterday there was quite a lot of talk about type system in Robert Wierding's talk, for instance, on languages on the BEAM, and Simon Thompson mentioned it a few times yesterday, and so forth. So that was more than I expected, actually. And there was some discussion about how and what and why about the type system. And now I'm going to give you all the answers. And I say that only half jokingly. So what I'm going to talk about today is that I'm in the process. I say I'm working on developing a type system for Erlang. And this talk is really, I want to show you the principles that I have for designing this and give you a flavor of what you can expect from that type system. And I'm really eager for comments from you. Whether you like something different, whether you think I made a bad choice, and where we can take this. So that's really the thing that I want to talk about today. I also have a tool in progress, but that's not going to be the main star. I'm going to mention it later in this presentation. Okay? Also, I know that we have a Q&A session afterwards, but I'm happy to take questions during the presentation if you want. All right, so I've started designing a new type system for Erlang, and a lot of people have tried and failed, or tried and come up with weird things, and this is a hard problem, and. So what gave me the hubris to try and do this again? And the answer is really gradual typing, which is a new development in the programming language community over the last decade or so. And I've tried to follow this development, and I've been really impressed at what they have. And my impression was that this could do something for Erlang as well. And so that's what I've been trying to do in this design. So I want to just give you a little bit of a background, and well, we've all been in these discussions, right? The static versus dynamic typing war, right? And should a language be statically or dynamically typed? And as Erlang programmers, we know that there are advantages with dynamic typings, right? And I don't have to mention this, but it's like programming becomes more agile. You're up and running faster, and development is just, the type system is not there to get in your way. And for Erlang message passing, the kind of open world assumption mailbox, then it's arguably the right choice. I mean, of course, you would like to, in specific system, you may want to have a way of talking about the protocols that you set up in one way or the other. But I think when Erlang was designed, I think it was the right choice to go dynamically typed for this reason. And also sometimes you have this issue where the type of a value really depends on runtime information, and that is handled gracefully or almost automatically by the dynamic typing discipline. That being said, though, static typing is useful at times, and I dare say it, I'm a Haskell programmer from many years. So I really like static types when they can help me, and they have advantages like they can catch bugs earlier, and when you have type signatures, they can provide documentation and they can help understanding, which is important when you have a sort of a large pool of programmers that need to work together. They help to organize the code, and they can help structure the code, and when you make architectural decisions, type systems can be there to help enforce those design decisions. And another thing that's often touted in the static typing world is that well-typed programs can't go wrong is the slogan. And of course, we all know that's not true, but there is a certain class of errors that we can eliminate with the use of static type systems. And that's a useful thing, even though you still have to write tests and so forth. This is a useful thing. You know, my personal perspective on this, the static versus dynamic, is that dynamic typing is particularly sweet for when you have small and script-like programs. Like when you start out, you want to have this agility that the dynamic typing provides. But as you grow larger, so I work at Ericsson, as I mentioned, and I'm working on the SGS and MME product, which is the oldest still active Erlang code base, I believe. It's 2.5 million lines of Erlang code. And when you have a situation like that, and you're 100 programmers working on this, spread over 4 sites throughout the world, you need help, you know, structuring the whole development. And so static typing, I think, can be an additional tool in that toolbox. I mean, we already have a lot of tools in our toolbox for handling with that, but static typing could be another one. And as I say, when you contrast these, the dynamic typing and the static typing, the different strengths, it suggests a way of programming that you start out in a dynamically typed setting, and as the project grows larger and you involve more programmers and you have a more complicated architecture, then you want to be able to add static types to this to help structure the code. But right now that's very hard because in programming languages you either have static or dynamic typing, right? So this is where gradual typing comes in, because gradual typing allows us to mix static and dynamic typing seamlessly and gradually. So specifically, it allows you to do this kind of development that I just talked about, that you can start out with a program that's completely dynamically typed, and as you go along, you can add types in a pay-as-you-go manner to get more static typing. So this is what the gradual typing provides. I mean, you can imagine different scenarios, but I think this is a very attractive feature of the gradual typing discipline. And there, as I said, this has been a hot research topic over the last decades, and a few languages have now come up. These are just some examples where they have included, in one way or the other, gradual typing. And it's interesting to see some of them are sort of dynamically typed by default or come from a dynamically typed sort of origin, but then they add static types like Python or Clojure. But then you have C#, which is a statically typed language where they've added a dynamic type to it. So you have different flavors. But you know, being Erlangers, we sort of live in this area. Also, PHP has a flavor called Hack that's developed by Facebook. And there are other examples as well. Okay, so I want to give you a very simplified introduction to gradual typing and the sort of main innovation ideas there. And there are details that I'm going to skip completely for the purpose of this talk. Otherwise, it gets rather theoretical. But I'm going to skip all that, and hopefully I will give a talk that you can comprehend. So the main thing about when designing a gradual type system is that you start out with a static type system, a fixed static type system, and then you add a type for dynamic typing. And then you need a way to talk about, you know, when types match or don't. And then you define what's called a compatibility relation. Okay, so let's talk about both of these things in more detail. So as I said, we need to start out with a static type system, and then for the dynamic type, I will write any here for the type that means dynamically typed. Okay, so this is now a special type. Okay, and then for the compatibility relation. So in normal static type systems, or the one that we start out with, types are typically compared using equality. And this is, even if you don't program a static type system, I think this is a quite intuitive notion, right? The type integer is equal to itself. It's not equal to Boolean, right? So that's pretty straightforward. So then we introduce the compatibility relation, which I write with this little twiddle or tilde. And if you have ordinary types from the static type system that you start with, compatibility works just like equality. Like integer is related to itself, right? But it's not related to Boolean, okay? The interesting thing happens when we have the dynamic type, the any type, okay? Because that is compatible with everything, okay? So it's compatible with any, and it's compatible with Boolean. And so the question is, why do we need to introduce this new relationship? Why couldn't we just use type equality and then just say that any is equal to everything? Well, the equality is an equivalence relation, and here is where it gets a little theoretical. Just because we have that integer is compatible with any and any compatible with Boolean does not mean that integer is compatible with Boolean. So we're lacking transitivity, the transitivity property here. So therefore, we need to have this separate notion of compatibility compared to standard static type systems. All right. Also, some static type systems have subtyping, and this is also something that I would like for my type system, so that's what I'm bringing up here. And you could imagine, it's very tempting to say, oh, first of all, I should mention, I'm using the colon to say is subtype of. This is also the notation that we use in Erlang already, so that's why I reuse that. So when I say T1 : any, I mean T1 is a subtype of any. That's how you should read that, okay? So it's very tempting to say that any should be both a subtype and a supertype of every type. But that also, and people have tried that in the past in order to enable mixing static and dynamic typing. And it fails spectacularly because we expect the subtyping relation to be a transitive relation also. So if we have this relation that T1 for any type T1 is a subtype of any, and any is a subtype of any type T2, then we would have a T1 is a subtype of T2. And so any type is related with any other type, and we wouldn't find any errors there because we don't have a case where they don't match, so we can't report any type errors. So instead, what we do, or what we have to do is to say, okay, any is just a subtype of any, and that's all there is to the subtyping relation. But then we're going to take the subtyping relation that we have and the compatibility relation, put them together in a special sauce here, which you can read if you like or not. And we get a new compatibility subtyping relation. Okay, there are technical details there. You don't need to understand them. But anyway, that's how it happens. Okay, and so I talked about this thing with static type systems, that they have this soundness that well-typed programs don't go wrong and so forth. We can't really say that with gradual types because they are not sort of completely statically typed. The guarantee is then that if a program fails due to a type error, then the problem lies in the dynamically typed part. So the new slogan is that well-typed programs can't be blamed. Yeah, that's Phil Wadler, for those of you who know this guy. He coined that phrase. Yeah, so we then have a situation where we can sort of partition our problem. So we can create parts of our programs that are statically typed, and we create this little bubble where we can be sure that here we don't have any type errors. If we get a if we get a runtime error that's due to a type error, then the problem lies elsewhere. Okay, in the part that we have not annotated so far. Okay. Excellent. So we have this. So that sort of concludes my introduction to gradual typing. So how can we translate this into Erlang? And here, I'm going to list a few principles that I've used to sort of translate this to Erlang. And here's where I really like some feedback, if you have it. You can certainly argue with these choices. Yeah, so my first design decision is that the static type system that I want to start off from. Remember, when we design a gradual type system, we need to start off from an existing type system. And so the first decision I made was to start out with the type specs that we already have, right? I didn't want to invent a new type language because we already have an established one, okay? It's rather rich, which means that it's going to be complicated to design the gradual typing system to accommodate all these features, you know. Not only does it have simple types, but it has subtyping, it has polymorphism, intersection, union types, and so on and so forth. So designing the whole type system is going to be a challenge with this design decision. But anyway, I think it's the right one, you know. I just have to roll up my sleeves and do this. Also because it's nice to have, once we get a tool out of this, it should work with existing code bases. And that's something, I mean, I want to be able to use this for our code base where I work. And so and we have a lot of type specs there. So I would like for my tool to work there. Okay? I've already hinted at this, but we need to add a dynamic type to the type system. And since I don't want to add, I don't want to create any new types, I want to work off of what we already had, I decided let's use the type any for the dynamic type. So any is now going to mean, in this type system, it's going to mean dynamic types. Also, the way that we use any normally in type specs in Erlang sort of mimics the idea of just having it being dynamically typed. So it doesn't feel like a sort of a big decision, to be honest. And then I sort of decided that this system should be based off of subtyping. And then term becomes the top of the subtyping hierarchy, and none is the bottom of the subtyping hierarchy. And if you have looked into the typing a little bit in Erlang, these are not sort of surprising choices. And as I said, I use the : to mean the compatible subtyping relation now. The subtyping relation that combines the ordinary subtyping with the compatibility relation. Okay, so whenever we write : we're going to mean compatible subtyping. And that's, again, a natural choice. And so we already have this notation for subtyping. So that's natural to include subtyping. But it's also that subtyping allows for more programs to be typed. So I wanted to have that in the type system. A caveat of these decisions is that any is now not equal to term in its how we use it. And that's the way it's going to be now. By the way, I mentioned this to Kostis Sagonas, and he gave his blessing for this decision. So I think I'm good there. So if you have any concerns with this, you can take it up with him. Okay, design decision 4. So and this is where we have sort of a real choice of you can do it in various ways, and this is the #1 complaint I get. But if you don't write any type specs, you get bog standard dynamically typed Erlang, right? And the idea there is that we should, this should not be a too invasive thing, this type system. If you write without type specs, you just get the Erlang that you know and love, all right? And there's no cost in enabling this tool, even when you have a code base that's free of type specs. You can always enable this. And then as type specs are added to the program, the program is checked against those type specs as you go. And it becomes more and more statically checked as you add more type specs. Okay? And this sort of mimics this idea that I had in the beginning of presentation about how to do development, where you sort of start out with a dynamically typed small program where you sort of is very nimble and agile, and then as you grow larger, you can add the type specs and you get more help from the type system. Yeah, but it also means that there's no type inference, which is something that you may want, okay? I haven't written that on the slide, maybe it should be there, but no type inference, okay? And some of you may miss that, and maybe I do as well, but I think it's the way, it's what you get from this decision. Okay, and another decision I made that relates to what I talked about earlier. Process communication will always be dynamically typed. Now I know you talked about yesterday, some of you, that you want to be able to maybe talk about protocols, and Joe talked about having protocols as sort of something that we can talk about in the language. And I agree with that, but this gradual type system will not solve that problem. Yeah. Okay, so I've made more design decisions, but they are on a kind of very sort of tiny level, and I think yeah, those are the most important ones. And so I'm going to go through some examples just to give you a flavor of what you can expect from this type. Just have some real code examples. And I'm going to use the append function here as a running example. Again, this was Kostis and I had a discussion about the append, so I've brought that in here. So we have the append function written in sort of bog standard functional style, and it has no type spec. And then we have it's used somewhere in this form, okay? And this will lead to an error at runtime, right? Sorry, no, it will not lead to an error at runtime. It's perfectly okay. That's the point of the example. I should learn my own slides a bit better. Thank you, Thomas. Okay, but yeah, so we have no type specs, so there's no error reported, and also there's no static checking, right? This is standard Erlang. But then we can add a spec, but we can say for all the parameters, they are dynamically typed, and the return type is dynamic. And this is basically the same as the previous example. There, I didn't add anything really of value here. Okay, so still nothing happens. Then we can say that all of the arguments should be list, and that we should return a list. Okay, and here is where the tool says, "Bam! This is not okay, because you've called it now with a 4, and 4 is not a list." Okay, so here's where you get a static type error. Okay, and I've used list here without an argument, which is the same thing as saying that it's a list where the arguments are dynamically typed, or the elements. Sorry, the elements are dynamically typed. Okay, so which is, but it's good to highlight that, because it shows that you can write these sort of partially static types in a gradual type system, which I think is a real power of it. You can say like, yeah, I want to be able to say that all of the arguments are lists here, but maybe I don't care about what the type the elements are, right? So I just say any. Okay, so that's one of the powers of the gradual type system. Okay. We can do other things, like maybe we didn't like that error that we got. Okay, so we just say for the final value, we just say, or the final argument, sorry, we just say it's dynamically typed. Okay, and boom, the static error goes away. And you see here that in the second case, we actually return a list. But here in the first clause, we don't return a list. We return the YS here. And why is this type correct? Well, YS is a dynamically typed. So when checking this, it makes sure that YS is compatible or subtype compatible with the result type. And it is, because it's any. So it is compatible with, or subtype compatible with list. And so that's why this example works out. Okay? So maybe this is the type that you want for append. Who knows? Or you can do polymorphism also, where you say, I want to say that the elements should all have the same type. And then, boom, again, you get a type error. Yep.
But if you were to call the append with an empty list and 4, would you get an error?
With the empty list and 4, yes, you would get a static error in this case. So the question was, if you call append with an empty list and 4, and that's
First clause.
yeah, so only the first clause will be executed in that case. But the type system doesn't care about what is actually executed. It only cares about what you've written, the type specs and the code. So good question, yes, but you still get the static error in this case, even if this would have been the empty list. Okay? Yes? Okay, so the question is, does A stand for any or for term? It doesn't, well, A stands for, okay, how should I formulate this? So I was almost about to say it stands for any type, but it becomes a little bit confusing. A can be, what's the synonym for any? It's a type variable. So this type variable can be instantiated with any static type that you like, okay? But if you use the variable to enforce that the elements of this list should be the same as the elements in this list, should be the same as the elements in this list. So it's the use of a variable. So A can be a type, some type. Yeah?
Does that include the any type?
Yes, it includes the any type, but
And does the system try to be as eager as possible to find a proper solution? Because it could always resolve to A being the any type, and then it could then nothing is gained by the spec, is there?
It is, because you're saying it has to hold for every instance of A, not just any.
yeah.
It has to take a pair of lists of instances from this.
Yeah, sure, but the system could always decide that it's enough for it to put A equals any.
No, it cannot. So, and this, so normally in a polymorphic type system, or when you do theoretical work on a polymorphic type system, you quantify the A by saying for all A, and then this type. And that means that this type is really a schema that you can instantiate with many different types. So it really means that you can have append of list of integers, and list of integers, or it can also mean the type list of booleans, list of booleans, list of booleans, or it can be the type list any. But the type has to be sort of interpreted that it can be all of those things. We cannot just cherry pick one particular type. So that's what the for all mean, okay? So that means that we cannot just decide to choose any here as A. It has to be valid for all the other instantiations as well. Does that make sense?
Yeah. Is it because the relationship that you gave to the
No, it's because of polymorphism, how polymorphism works. Yeah. Yep.
So to concretize the question, what if you change the 1 in the first argument in the list, the first list element of
Yep.
of the actual call? Let's say you exchange it with A as an atom.
Okay.
Would that go here?
Yeah, so the question is, what if we remove this 1 here and replaced it with an atom? And this will be reported as an error, because those two, so the atom will not have the same type as the 2, but it's required by the use of the type variable here, that all elements have to be of the same type.
Are they both terms?
Sorry? They're both terms. So if you had written list of term, then it would have been fine, or it would have been not a type error. Indeed. Sorry, can you repeat?
If a fallbacks to any, then means like atom is any, and 2 any, and 3 any. Like the whole list can fall back to any.
Yeah, but it's the for all.
What do you mean by A can fall back to any?
Like a variable, a type variable,
Yeah.
and if like the system can decide that it's any, then
No, it cannot decide that. That's how polymorphism works. It cannot cherry pick and say, I just want to use it at this type. It must be compatible with other instantiations of A as well. That's the thing.
Another word to use here is that it's generic.
Yeah.
You can fill in whatever you want for A.
But I think in some languages, if you're fallback,
Okay, I'm going to stop you there because I'm running out of time. Sorry, but I only have 10 minutes left. So, and I want to get. I have a lot more juice here. So, okay. So, yeah, this was clearly fun. But okay, But this is a cool example also that Kostis gave me. So, so here we can say the second argument is a union of integer and list, which means that it can either be the type integer or list. And the result can also be that. I mean, they have to be. And so here we're sort of trying, or I shouldn't say trying, but we can again, we are allowing integers in the second argument and allowing them to be returned. And again, that's a way for this program to be well typed statically. Okay? Does that make sense? Yeah. You can argue that this shouldn't be an OK type because it might be cases where we're not actually returning an integer, like in this case. And the tool that I'm working on, it doesn't do exhaustiveness checking. So it will not catch this particular case. And you can argue whether it should or not. But it doesn't report an error in this case as of now. All right, so I've been talking about this tool, and I just want to say a few words about it. I'm calling it the Gradualizer. Oh, you like that? I'm pretty pleased myself. So I just want to have one status slide, and it's ongoing work, and it's still sort of alpha quality. So it's a little bit hard to use it on your current code base. Because it can still handle a sizable subset of the type system that we have already. You know, there's plenty of stuff in there, but there are also some stuff, and the most important things is the polymorphic subtyping and intersection types. Those are not in there. But we're 2 people that are currently hacking on it, and contributions are more than welcome. It's on GitHub. It's open source. So please have a look. It's very rough at the moment. It's not, it's not set up to be, it just works for me and Victor, who's hacking on it. So be aware of that. But yeah, yes.
What license did you put on it?
MIT. Yeah, I know. I know. Okay. Yeah. I should have gone to yesterday's talk before I started this. Okay, so here is a question that you've all been thinking, right? Why do we need the Gradualizer when we have the Dialyzer? So first of all, the Dialyzer is not a type system, okay? And you've heard this many times, but in this talk it's particularly important to emphasize this. It's a discrepancy analyzer which tries to predict runtime errors. And it avoids false negatives, so it doesn't want to be wrong, right? That's what we usually say. The Dialyzer is never wrong. Well, the downside of that is that it's almost never right also. So, and also it doesn't use the type specs to guide the analysis. It just infers information and then checks it against the type specs. And so the Gradualizer has taken a completely different, and you can argue complementary design to how to deal with this. Okay, so I think of these tools as rather complementary. I'm going to show you a couple of examples just to give you a flavor of. Yeah, thanks. the differences and how they look. And these are sort of yeah, they're Mickey Mouse examples so that they fit on the slide, but they're distilled versions of most of them are distilled versions of real stuff that we've encountered. So one thing is that so this example is where you have a spec and the return type is the empty tuple, but the one of the clauses doesn't return a tuple, right? It returns true. Okay, so that is inconsistent with the spec. And Dialyzer will not complain about this program at all. It's only when you add the over specs that it will detect it. But this is a clear case for the Gradualizer to say, no, this is an error. Okay? And that's because it's the Dialyzer is not sure whether this is going to execute. It doesn't sort of enforce the specs. Whereas that's what the Gradualizer does. Another thing is with unions. So here we have a function that can return a union of tuples. So we can either return the tuple undefined and binary, or we can return the union the tuple integer and undefined. So those are the two tuples that we can return. The function actually returns a third tuple, which is not among those, which is undefined. Okay, and the Gradualizer, the Dialyzer doesn't find this error, and that's because it approximates unions of tuples to tuples of unions, which is a more approximate thing. Okay, so it passes. So it approximates it to this. So you have a tuple of undefined or integer and binary or undefined, and this tuple is compatible with what we're returning here. Yeah. One of the things that the Dialyzer is really good at, but the Gradualizer doesn't do, is have this flow sensitivity. So we have a function bar here that it takes in two atoms, apa and bepa, which is sort of common Swedish, default values, and can return true and false. And here it's only called with apa. And one of the things that the Dialyzer can do is just to figure out that, the bepa case is never taken, right? So it can figure that out, and if you use the Wunderspecs flag, it will say that false is actually never used. So that's quite clever, actually. And Gradualizer can't do any of that. It doesn't do any of that. Okay. And a final thing here, which maybe is a cheap shot at the Dialyzer, but it has sort of a built-in limit on how deep into types it will go, and this has to do with that the problem that the Dialyzer is trying to solve is actually very computationally expensive, and they just want to make sure that they finish before we have to go home for dinner. So the first example here, we have you return a nested tuple, and the final element here, the 5 and the 4, they don't match, and the Gradualizer can catch that. Sorry, the Dialyzer can catch that. So can the Gradualizer, of course. But then if you add one more depth, one more nested tuple, then the Dialyzer fails to hit that. And this is due to sort of that they have a fixed limit on how deep they go. Though in fairness, this is not a big problem in practice, but it is a difference between the tools. Okay, how am I doing for time? Okay. So I'm basically done. So I just want to thank Victor Söderqvist, who's helped me a lot with the hacking and discussions, and David Wahlstedt, who's been pushing me to pursue this. So I just want to acknowledge that. And that's it. Thank you very much.